Told you we would open each class. Going into the review, since week 1 is already done, I'll check week 2. Period 4. Homework help. And nothing is posted. So this next assignment, also 8th grade, it's a biggie. It's a big one. When is it due? Next Monday. That's Monday, 11:59. Which is after your quiz. I would hope you would have it finished before the quiz, but it's after the quiz. All right, we'll move on then to the notes then. So reflections. All right. Similarly to rotations, performing a reflection. What's a common word for a reflection? If I wanted to just use like a regular English word. Yeah, a flip. If I wanted to perform a flip. Okay, can you take this through? It mostly involves either switching around coordinates, like we did yesterday with rotation. It could possibly let's say, have to do with that, like it might have contained that, or possibly changing a sign. So that's something similar to yesterday. You're gonna have to follow rules, but at most that's what you'd have to know how to do is when to switch an x and a y, when to change the sign from positive to negative or negative to positive. Okay. Unlike a rotation, reflections occur about an axis. When I rotate, which is what we did yesterday, if I perform a rotation occurs around a point of rotation. Whereas today, a reflection occurs across an axis, across a line. And when you flip a point over a line, the distance, the perpendicular distance between the pre-image and the image, wherever that point started and wherever that point ended up, it should be equidistant from that line. The good news is on these, we're only going to have to learn these 4 axes of reflection. We're not going to do anything else. For the point of rotation, yeah, a point of rotation could have been anywhere on a plane. But I also did give you a little bit of help when I said, okay, if you had to pick the most important point of rotation, what's the most important point of rotation for you to know? Meaning that would be the most likely to show up on a quiz or a test. The origin, yeah, and you can even argue that's the easiest one. Because then all you have to do is maybe change the sign or switch some coordinates around. But yeah, that's the most important, but technically you could be asked for any point of rotation. For reflection, you're only going to be asked for to flip over these 4 different axes of reflection. So just like we did yesterday, let's look at this table and let's compare and contrast. Ms. Sam, were you able to ask about this, about if they're going to have like a reference sheet or a note?
Not yet. Yes, I will find out.
So we're going to assume that by Friday you're going to have to memorize these. Let's start off with the axes. An axis is a line. In Algebra 1, you learned about the x-axis, which is horizontal, and a y-axis, which is vertical. Where do they happen to meet at? Just for a bonus question. What's that point of intersection of the axes called? Again, the origin. Yeah, sure, 0, 0. So what happens if you get any point and you were to flip it over either the y-axis or flip it over the x-axis, where they would have to be equidistant? Well, what do the images here, what do the afters both have in common? If we look at both of those, what do they both have in common? Okay, but I would actually argue that's more of a difference. You're going to see negatives here. X and Y stay in the same position. Okay, we don't have to switch the X and Y. That's the first thing I would want you to notice. So flip over an axis, leave the X and Y where they're at. That's what they have in common. When you study something, at least me, the way my brain works, I want to first try to group things according to what's similar, and then after I know what's similar, try to figure out what makes them different. So if I'm flipping over an axis, the X and Y are going to stay where they're at. Okay, but yeah, what's different? And don't just say negative. Let's say it better like we did yesterday. When you stick a negative in front of an unknown, what does that mean? And I asked you to write it down, even though you didn't see it. I might have even written it on the board for this class. I think I wrote it. It starts with change and ends with sign. Change the sign. That's what the negative means, to change the sign. So if I flip across the x-axis, which one single coordinate is going to change sign? The y. Mm-hmm. The y. If I flip over the y-axis, which single coordinate is going to change sign? Okay. So we'll memorize that. Okay. Now, the last two axes of reflection are diagonal lines, but they also happen to pass through the origin coincidentally. You might remember this from Algebra 1, you may or may not. The line y equals x is a diagonal line that passes through the origin and goes up right and down left. Up and to the right, down to the left. This is y equals x. The line, because that's what an axis is a line, y equals negative x, also passes through the origin diagonally at a 45-degree angle. But now this one goes up and to the left and down and to the right. And these can also act as axes of reflection. So now let's compare and contrast those two rules. If you have to flip over either y equals x or y equals negative x, what do both of those have in common? Both of them require you to change the position of x and y. The y becomes the x becomes a y. The first number, the first coordinate you see becomes the second coordinate becomes the first one. They both require you to flip the x and the y around. But the difference is on y equals x, where you don't see a negative, these are things you can use to remember, where you don't see a negative, what happens to the signs? What happens to the signs? They're the same, nothing happens. Just switch x and y and that's it. Nothing. On y equals negative x, where you do see a negative, which after you've flipped them, after you've changed the x and the y around, they both change sign. They both change sign. On a side note, so I was talking with a co-teacher in the other class, and so one of the things that she was discussing was whether or not these can be printed out, or whether or not even I should be printing them out. But I'm not gonna print these things out for you, because I see some of you guys have nothing in front of you. In a perfect world, you would write these in your notebook. I floated the idea at a bit meeting, at a geometry meeting, about being able to use notes on quizzes. It's not gonna fly. It's not gonna happen. So to me, that limits my ability to dictate to you how to maintain a notebook. So, really, I'm at the point that, you guys do whatever makes you feel comfortable. I know that I asked you for one of these because in a perfect world, you would have your notebook and you would, write everything down in here, whatever. But if you feel that you want to print these, I'm not going to print them out for you, but these are available for you. If you want to print them out on your own and either staple them into this thing or keep like what Luna has, in binder or folder and keep them in there, and you want to do that, whatever. I know. I'm just saying, like, I just want to throw that out there because what I don't want is you guys just to have nothing in front of you. Everybody knows where to find these, right? Okay. All right, so let's go to some examples. These examples I don't think should take that long. You're the first class I do it with, but that'll hopefully at least allow us to start dilations today. On this example, what are we being asked to do? Reflect across the x-axis. So let's memorize this, hopefully without being able to look down at the paper. An x-axis reflection, which is either going from top to bottom or bottom to top over the x-axis. What are we remembering to do for, just like with a y-axis reflection, what do they both have in common? What do they have in common? The x and the y stay exactly where they are. So if they're going to ask us to flip these, hey, look, this says 3, 2, so cool. 3, 2. This says negative 1, 3, negative 1, 3. This says 1, 0, perfect, 1, 0. They stay in the same position. But, now how are they different? One of the coordinates has to change sign. Which one? If it's an x-axis, the y. If it's an x-axis reflection, the y changes. If it's a y-axis reflection, the x changes. So here on the y, I had a positive 2, I need a negative 2. Here on the y, I had a 3, I'll put a negative 3. And is it possible to have a negative 0? No. Oh, but wait, you just made them all negative. No, it's not going to make them negative. Change the sign. If they would have been negative, I would have made them positive. I would have just used my eraser and erased the negative, so they would be positive. So, what seems to be the rule, which really that can be just answered here. I guess if you were to do it verbally, you would say change the sign of the y. That's really what you did if they were asked for it verbally. But this here is what was it was shown to you on the first slide. What is the rule in arrow notation or coordinate notation, whatever you want to call it, for an x-axis reflection? The x stayed the same, and the y changed sign. I'm just rewriting what's on the first page. I'll graph these just for this first example, but one of the things I realized yesterday, I think I'm giving a disproportionate amount of time to the graphing aspect of this, and I think that's stuff that you should know heading into. Does anybody not know how to plot points? I'll do it for this first one because I think it's a good visual aid. You can actually see the points flip. But after that, I think I'm just gonna stick to following the rules.
Because their quiz, y'all will have to,
Yeah, but I mean, I would hope you know how to. So like, look, let's plot the pre-image. 3, 2. That's right here. They didn't give that point a name, so we won't give it a name. Here, let's go one by one. Let's do that. Now let's do the image, which is the second one. 3, negative 2. What can I tell? They are both equidistant from what axis? They are both equidistant from what axis? The x-axis, yeah, that's where they flip over. The red point is 2 boxes away. The blue point is 2 boxes away. Here, the next one, negative 1, 3. What did we get after that? Negative 1, negative 3. What can you tell me about those 2 points? They are equidistant from the x-axis, yeah. 1, 2, 3 boxes away. 1, 2, 3 boxes away. One, 0. Sorry, 1, 0 is here. What would happen if I were to flip that? This is actually good. I'm actually glad I drew this. But wait, the image also says 1, 0. Yeah, because if it's on the axis and you flip it, it just stays on the axis. There's nothing to trip over. It's just staying right there. If a point lies on an axis of reflection, nothing happens to it. It just stays right there. Any questions here? Okay, the next one. What are we going to reflect across? The y-axis. What did we remember? What does the x-axis have in common with the y-axis? Leave them in the same position. So again, 3, 2, negative 1, 3, 1, 0. But now what happens? Change the x. So this 3 becomes negative. The negative 1 becomes positive. So I just erase the negative. And then make this one negative. Okay, this one I won't graph, but if you want to graph it on your own time, feel free to do so. If you feel that you're seeing something weird, come to me during my office hours and I'll show you. We'll see what's going on. But I'd rather just stick to the rules. But now, with that being said, if anybody seriously does not know how to plot, raise your hand and let me know. I'll plot them for you. But considering we have a limited amount of time, I think it's best spent on this stuff on the new schedule. Describe the rule, okay? Negative x, comma. No y stays the same. Nothing happens to the y's. Ryan, how we doing back there? Jamal? Okay. This next one, what line are we reflecting? We're reflecting over y equals x, which, just to give you an idea, that would be the axis of reflection. So if I were to graph them, these would look like mirror images of each other in reference to that line right there. What was the common rule that we remembered? Whether it's y equals x or y equals negative x, what do they have in common? Flip the x and the y's. So like instead of 3 and 2, I'll put 2 and 3. Instead of 1, negative 1, 3, 3, negative 1. Instead of 1, 0, 0, 1. That would be after the flip. Now, after that, see, because that's what this has in common with y equals negative x. But then after that, what do they have that's different? That in this case, I leave it that way. I don't have to do anything else. On the next one, I'm going to have to change all the signs. But here, I will just leave it. Do you want me to graph these so that you can, if anybody, I'll graph them so that you can see how they look. Here, I'll do one of them. Maybe watch. Let's do 3, 2, and 2, 3. So at least you can see one of them. 3, 2, and 2, 3. If you were to measure, they would be the same distance from that blue line. Remember that it's hand drawn, so it might be slightly off, but trust me that it is. What was the transformation rule here? Just y and then x. Yeah. Just switch the y and the x, nothing else. Jamal, did you switch the y and the x? I heard that you're excellent at switching y's and x's. And this should be the last slide. Same points, but now y equals negative x. What does this have in common? So that you don't have to memorize so many things, we want to categorize this in our head. What does this have in common with the last one that we did? Switch the x and the y around. That I know. That's to make it simple. Every time I see y equals x or anything like that, I know I'm going to change around the x and the y. I'm going to change the position around. So 2, 3, 3, negative 1, and then 0, 1. But there was a difference. Now all the signs change. They don't all have to be negative, but they all have to change. So this becomes negative 2, negative 3, negative 3, Oh, I had a negative on the 1? Positive, yeah. Can't have a negative 0, so that's going to stay the same. And then this one become negative 1. What would the rule be? As was shown to you on the first page, this would be negative y. All this is asking you for down here is to summarize our results, which we've already done on each slide, but where else did you see a summary of all our results? Where do you, assuming you write down notes, where would that already be in your notebook? Where did you see what's supposed to go there? On the first slide. It's the same thing. I think that's it. Yeah, it is. The same thing you saw here, even though I messed it up with a bunch of circles and stuff. Any questions there? Okay, so then that's it with reflection. That is reflection. How many transformations have we learned about so far? Or tried to learn about? 3. What was the first one? Translations. What operations did translations involve? Adding and subtracting only, yep. Then you were like, oh, that's the easy one. Then came, rotations. And yeah, that's a lot of stuff to remember. Now, luckily, if you're rotating around the origin, which that's mostly what you're going to have to do, that's not too bad, but you still have to memorize. Okay, you have to compare and contrast and memorize. Hopefully, we can review a few of those tomorrow. And then finally, then today we did reflections. Okay. Now, what we should have been doing today all along, according to the calendar, is dilations. So that's good. We can get into that one now. Now we can get into dilations. And then, even if we don't finish today, we finish tomorrow. Anytime we have left, we'll review. If I'm being responsible about things, which one do you think I'm gonna probably want to spend the most time reviewing? Translations? Nah, I don't think so. You tell me. Let me get your feedback. Which one would you say has been the most challenging so far? The one that you've understood the least? Yeah, rotations. Yeah, that's probably what I'm gonna spend the most time on. All right, let's see. This is probably gonna crash on me, but let's at least try to. Let's see who really wants to impress me here. How does a dilation differ from all the other transformations that we've learned about? What's different, Jaden? What's different? Huh? Say it better. Charles? No, Chris. I want to call Charles. Yeah, but there was a name for that. Jamal? Reduction. That's what I'm asking you. I know there's a yeah, you were. You have the notes. I didn't know there were any of these bigger or small. Everything is bigger. What were your original plugins? It would have been actually. Oh, you know what? That was the day you were after. You didn't write down those notes online.
Shrink and expand. Dilation occurs when you enlarge and reduce a figure. Shrink.
I'm starting to have doubts.
I didn't know there was a certain word.
This is one word that we can't figure out.
All I know is that
Can you just tell us something?
change size.
Oh man. You're the teacher. You're supposed to give us all the answers.
That's not what we're saying, but we're struggling, okay?
So let's find it together.
Does
It's
it
more rewarding this way.
dilute you? Was it a second phase?
It was on the first
Friday.
and there you go. It crashed.
What school did you come from?
Do I?
I came from a different state.
What state?
Florida.
No.
And they're not allowed to have Sharpies?
At the school I was at, yeah, I apologize for that. That was just habitual. I trained myself to look for Sharpies and stuff, and but if they allow them in school, then again I apologize for that. But yeah.
I don't know. Yeah, that's exactly why. Shut up. Who said that?
The same way that you guys are, the same way that you guys are struggling to learn and memorize transformations, I have to learn a new set of rules. So, can you now answer?
Multiply. I heard it. I heard someone say multiply.
The properties of
Say that again.
properties of rigid
Dilations are the only non-rigid motion. The other three are considered to be rigid motions. A dilation is a non-rigid motion. And then Jade now would say, well, hey, can you tell me in paraphrase, can you just give me in common words, what happens in a dilation that doesn't happen in the other three? And then she would say, yes, size and shape are not necessarily preserved. You're allowed to change size. Now, yeah, if I wanted to take it further, and I'm sorry, you do really want to. I forgot that. I haven't read your name yet. Yeah. Josh. So, I asked you, hey, what operations are we doing when we translate, add, or subtract? What operations are we doing when we reflect? Yeah, technically we're multiplying, but it's really just by a negative. That's where you saw sometimes the signs would change. Okay, that's what that's caused by. But now with dilations, now we actually get into multiplying and dividing by numbers that are not just 1 or negative 1. And it's going to crash on me again. Every time I open a new file, let's see. It crashes. Okay, so these are just some facts for dilations. To get through this, I'm not going to bore you, but I'll point to the key ones. I heard some of you just reading this before. These are good words to know. Reduction, enlargement. In algebra, we call these stretching and compressing. Scale factor is important. I guess that's why it's underlined. And even though in practically, like when it comes to actually doing these, it might not be that important to know this, but when you dilate, you have a center of dilation. What does that sound like? That we've already heard. Center of rotation. When we rotate it around a point. When you dilate in reference to a point. Unlike a reflection, it's not a line, it's a point. Okay. The good news for you is that, look, number one, these are probably, as far as the transformations go, yeah, I don't know if I should be telling you this or not, but this will be probably the one that you'll be least asked about. But if you are asked about it, most dilations will occur around the origin, just like with the rotation. So that's the good news. But the bad news is, I have to teach you how to dilate around other points as well. This word similar, that's important, but not really yet, because we haven't done similar figures yet. So even if I try to explain it, it's probably not going to make too much sense to you. So I'd rather worry about that later.
Yeah, and I think when we do the similarity unit, we get more into a little bit more into dilations then.
Now here, let's make an association before we move on from this page between scale factor and those two. On a reduction, I don't know, let's use an F, I guess, for factor. The scale factor, I'm just gonna use an F for factor. Technically use whatever letter you want, I guess, but on a reduction, the scale factor is between 0 and 1. What types of numbers fall between 0 and 1? Proper fractions. A fraction where the number on top is smaller than the number on the bottom. On an enlargement, oh God, I'm getting more, every year I get worse. I was my 5th grade spelling bee champion, and I think since 5th grade I've gotten worse at spelling every year. I should put that on my bio. 5th grade spelling bee. Enlargement.
I should see pencils going as he's writing this.
The scale factor is greater than 1. What is a scale factor? Well, on that last slide that we saw, that we said, what operation are we going to be doing when we dilate? Multiply or divide. This is the way that this is being expressed to you here. This is in terms of multiplication. Just assume multiplication. Dividing and multiplication, those are reciprocals of each other. Let's just assume here that we're talking about strictly multiplication. That's when these rules apply. It's the number that you multiply by. That's the scale factor. Okay, so here, let's do some examples here. The following coordinate plane shows a dilation of rectangle ABCD with a scale factor of 2 and a center of dilation at the origin. The result of this dilation is a, they just want to know if it's a little vague and I don't have a key to this, but I'm guessing by the wording they just want to know if it's an enlargement, what do they call it, or a reduction, sorry, I'm used to algebra. Look, it's hard to see, but the primes, these are the primes, these are the images up here. And if you can't tell, even if they didn't draw the graph of it, you can tell by the rule, what am I multiplying by? Is 2 in between 0 and 1, or is it greater than 1? So is this an enlargement or a reduction? Yeah. We started with a smaller rectangle, it got bigger. How much bigger? Twice as big. I'll teach you a little secret now, just so that, because I know I'm not going to get to it today, but then we'll see who remembers it tomorrow. If ever you want to know where a center of dilation is, the very last question on this slide asks you to find the center of dilation. Draw a line between the image and the pre-image, and all the lines should intersect. Now, here they tell you that it's at the origin, so we already know the answer. But to confirm that, like get B prime and draw a straight line between B prime and B. Draw a straight line between A prime and A. I'm doing this by hand, so draw a straight line between D prime and D. Draw a straight line between C prime and C. Even though it's a little sloppy because it's hand drawn, can you tell where they're crossing at? Where all 4 of them are crossing? I know it looks a little bit off to the right, but give me a break. I'm drawing this by hand. If I had a line tool, yeah, it'd be at the origin. That's how you can determine. What other questions here will ask you that? Okay, let's dilate JKL using a scale factor of 1/2 and a center. See, look at that. Whoever made the slide, I didn't make the slide even. That is a mistake there. What should that say instead? Dilation, the center of dilation. Because the center of dilation is at the origin, just like with rotation, what that means is no extra adding or subtracting involved. We're going to have to do extra adding and subtracting when that changes. So in arrow notation, I start off with every xy, arrow. What's the scale factor? 1/2. So we're going to have 1/2 of an x and 1/2 of a y. That's the rule. 1/2 times each x, 1/2 times each y. Look at the scale factor. Is 1/2 in between 0 and 1, or is it greater than 1? It's what? Harvey? Yeah, it is between. So it's going to be an enlargement or reduction. It is a reduction. And then how can you determine if it's a look? Hey, we just did this. How can you determine if we have an reduction or enlargement before you? I have not graphed yet. So how can I tell? No, that's if I want to look for a center of dilation. Here, I'm being asked reduction or enlargement. I already answered that question. But how was I able to do it without graphing? What did I look at? The scale factor. Okay. Let's actually do the dilation, and that'll be it for today. We gotta get each of these points, so we gotta see where they're at. So let's do K first. K presently is at 0, 3. Okay, so K prime is gonna be at 0 times 1/2 and 3 times 1/2. Oh, I already wrote it.
So you just multiply the scale factor times each x and y.
So 3 times 1/2. So K prime, the new K is what? 0 times anything? 0. Comma. It's okay. Yeah, it is gonna be 3/2. That's what I wrote, but that's probably gonna be hard for you to plot. So just use the decimal, I guess. You can always round this if you need to, but here you don't have to round. This is 1.5. So where's 0, 1.5? It's a box and a half above the origin. That's gonna be K prime. Okay. Let's see. I don't know. I guess let's do J next. So J is at -3, 0. So that would be J prime would be at -3 times 1/2 and 0 times 1/2. -3 times 1/2 is? If 3 times 1/2 is 1.5, what is -3 times 1/2? -1.5, and I still have a 0 on the side. So that's going to be here. This is J. Let me just keep it in there. And then finally the last one, L. L is at 2, -2. So L is going to be at 2 times 1/2 and -2 times 1/2. What's half of 2? 1. So L is going to be at 1 and then -1. Or L prime, I'm sorry, L prime. So that is here. If you connect the dots, what have I just drawn? I've drawn a triangle that's half as big as the original one.
Questions?
Any questions about that? Tomorrow we'll finish dilations. I'll try to review as much as I can before the quiz. Obviously, there'll be a focus on rotation. You might want to go back and write down all the notes from transformations, have them in the notebook. Make sure you also work on your assignment. That'll be it. You can sign out.
You don't have any paper thing for them to like practice on tomorrow or anything?
What I was planning on doing is